Our next speaker is Maguette Toure. She is a 5-year experienced data scientist currently working at Nokia, telecommunication equipment provider for the last 3 years. Maguette's area of work at Nokia is around building AI and machine learning models to predict and troubleshoot network issues using various types of data as performance KPIs. Alarm data, log data, configuration data, and so on. One of the machine learning solutions she designed and developed about configuration recommendation is patented. Before Nokia, Maguette has worked for a company named Bourbon, offshore leader in offshore services for oil and gas companies. There she worked on predictive maintenance using sensors data and fuel consumption optimization. Maguette has an engineering degree in mathematics and modeling from the French school ENSA, Toulouse, and is originally from Senegal in West Africa. Maguette, thank you for joining us. We're excited about your talk. Let's start, please.
Thank you, Mashal, for having me. And while I am really honored and excited to be part of this Woman in Data Science event. So let me share my screen. Okay. So I am going to present you today a project in which I am working on currently and for the last year, which is about alarm cause analysis for Nokia telecommunication network. So I will start with giving you a little bit of context about the project. So what was the business decision? How was it addressed? With which data set? And then I'll walk you through the solution, which is composed by two modules, an alarm causality graph and a pattern extraction modules. And then how both of these modules are used to propose cause analysis for this project. So on this alarm cause analysis project, the business problem is to isolate alarms that are related to a network incident. What we call a network incident is in fact one or a set of alarm. In fact, on a network for a given customer, we have flow of alarm coming up, and sometimes we can have really critical alarms that need to be fixed quickly. And this alarm will trigger an incident. So to address this issue, we are using as data alarm data, of course, with information about alarm IDs, alarm name, and so, and also with alarm start time and end time, which we will also call alarm clearing time. The alarm node, that is the type of equipment on which the alarm is observed, the family of component, and also the city in which this component is. And we will use also what network topology relationship that are really essential on network equipment. In fact, on network equipment, some will communicate, right? And well, an alarm on one component can have a cause effect on another component, and some will be completely independent. For example, on this case here, let's say that we have 3 machines M1, M2, and M3. And while M1 can communicate with M2 and M2 with M3, but while between M1 and M3 there will be no communication and no causality whatsoever. So the approach chosen to address this cause analysis is composed by two solutions. So an alarm causality graph and a pattern extraction module. So for the alarm causality graph, we are using a patented solution from Nokia Bell Labs, which is an internal research team inside Nokia. And while this DIGDAG graph proposes a representation of spatial and temporal relationship between alarms. So what we call the temporal relationship between alarm is, for example, for a given machine, let's say M1, we will say that an alarm A have a causal relationship with an alarm B, shown by this red arrow, if when the alarm A have started, before its end, a second alarm B start. So this is a temporal relationship, and we will also consider the spatial relationship, which is showed here by the green arrows. So for the spatial relationship, we will use the network topology that we have. So as M1 will communicate with M2, there is a potential causality between an alarm A coming in M1 and a later alarm D coming in the machine M2. So all the causality in a time window are well translated into a word, let's say, that is composed by a symbol. And while this word, in fact, will be used to render a graph with the DIGDAG methodology. So how this word is built, in fact, we will take event by event. So but the symbol will be the alarm ID when the alarm start, and the alarm ID with a sharp character when the alarm ends. So on this particular case, the word will be A, as A has started first, and then D, then B, then C, then E, and then the next event is the end of the alarm A. So we will have an A sharp to the word, and then G start, and then B end, E end, and so on. So like this, in a certain time frame, we will be able to have a word to render the DIGDAG graph. So I will give you an example of a DIGDAG graph with a certain word. So let's say that we have first an alarm C coming in the system. So we will have a vertex C that is connected to the root of the graph. We will say that C can be its own cause. And then if an alarm B come into the loop, as alarm C was still active, we will have an edge between C and B, meaning that C can be the cause of B, or B can be its own cause. As here we can see it is linked to the root. And let's say that now C is well not active anymore, so has ended. Then we will deactivate this vertex, so it is turning blue. Then an alarm A come into the loop, So as C is not active anymore, we will not have an edge between C and A, but we will have an edge between B and A, and also between the root and A. And C comes again into the system, so we activate C again. Then A comes inactive, so has ended, so we deactivate it with this color. And B, the same. And then a new alarm D come into the system. And as C was the only alarm active before, then we will have an edge between C and D. And well, D will also be linked to the root. And now we have an alarm B, a new alarm B coming. So what we will do is to activate the first alarm B, and also to create a new one, because in fact if we keep only this vertex B and connect this alarm D to this vertex B, in fact we will generate a causality chain that will go from D to B to A. Which is not something that we have observed. So that's why we are creating here another vertex B to show that D can also cause an alarm B. And now C is deactivated, so we add that, and D also. And the alarm A is active again. And as the alarm A is active again after the alarm B, then we can have also an edge here that is represented here. So well, after D we can have B, and then D can end, and then A can come afterwards. And A is deactivated, so it's turned blue, same as B. So the two vertex of the alarm B are deactivated. So in fact, this is how we are building the DigDag graph. And the main objective, having an incident, well, when we apply this DigDag graph, we will have all the causality chain that are happening in the time window around the incident timestamp. So let's say that our incident alarm is the alarm A. We can have all the path that can lead to the alarm A, and well, be able to take an action maybe on the predecessor of this alarm A to have an impact on the clearing of this alarm. So apart from this first graph solution, we have a pattern extraction module, which is taking as an input alarm sequences. And for this pattern extraction, we are using the FP growth model that have the advantage to be scalable. So, and we are doing an intranode and an internode pattern extraction. So in fact, intranode means that we will focus on the alarm that are on one component only. So figure out what are the rules within the alarm of the component itself, and also internode using the combination of the alarm on two connected components. And to generate those alarm sequences, to generate the alarm sequences intranode first, in fact, we will just take all the alarms that are happening in one component. So let's say that for M1, the alarm that are happening in a time window are the alarm A, B, C. And in fact, we will drop all the duplicates, and the order also will not matter, to extract the pattern and rules. And we will also generate the alarm sequences internode, with respect to the network topology. So, and well, for this, we will take the alarm happening in two connected components. So, and well, we will drop all the duplicates inside and take the set of alarms. So, without taking here also into account the order. And to give you an example of the pattern and rules that can be extracted with a simple example, we have here a set of 6 alarm sequences, and a pattern can be extracted and rules. We are more interested in the rules on our case. In fact, the rules will say that having this set of antecedent, we can have on the same alarm sequences, and well, no matter the order in it, this consequent with a certain confidence score, which is the probability to have the consequent having the antecedent. We also have a lift score and a support score associated. So the support score is the frequency of both the antecedent and the consequent. So, well, divided by the number of total alarm sequences. And the lift, in fact, is a score that measures the trust we can have on the confidence. So the higher the lift, the stronger we can have faith in the confidence score. And well, when the lift is lower than 1, it means that, well, we cannot trust a lot the confidence score. So let's say that for a consequent, it is really coming a lot. For example, we can have a confidence that can be high only because, in fact, the consequent is coming a lot in the alarm sequence database. So how we use this rule for an incident is that we will take the incident alarm we are interested in, and we'll try to find all the antecedents that can have as a consequence this incident alarm. So let's say that we have an incident with the incident alarm being a DNS proxy is unreachable. Then we will figure out, we will in fact extract all the rules that are associated to the incident alarm and have alarm in the short time window before the incident alarm. So let's say that we will see a certain number of them. We will have, in fact, the associated alarm to that incident alarm. And this associated alarm, in fact, can be a potential cause to the incident alarm, because it will say that having this associated alarm, there is a certain probability to have in the same sequence the incident alarm we are focused on. So to maintain the rule database, we are doing a retraining on the monthly basis. In fact, so to catch every time the new rules that can be generated, as the network can change, new alarm can come, new remove can happen, and new issue, in fact, can happen. And also, we remove the old rules that seems to not apply anymore. So if a rule was extracted, I don't know, 6 months ago, and well, for 6 months after, on all the retraining, we didn't extract it anymore, then we will drop this rule. So this is a schema, so a very simple schema to explain how this pattern extraction is working with the training and the model application. So well, from the alarm data history and the network topology, all the alarm sequences are created, and then the pattern are extracted. So the pattern and rules, they are extracted and saved. And then later on, every time that we have an incident, we extract the incident alarm information, all the alarm coming around the incident timestamp, to generate the alarm sequences that we have, and we will compare the alarm sequences with the rule that was learned to see if we have some match. So the two module, the alarm causality graph and the pattern extraction, will work together to propose a cause to the expert, so the network engineer. So what we will do when we have an incident is that first we will render the alarm causality graph, and we will highlight the incident alarm in an orange shade, and then the rules associated to the incident alarm as a consequence will be extracted by comparing the current flow with the learned rules. And when we have a rule that match path on the graph, right, we will highlight the associated alarm in green as being the most probable cause alarm. So we are coming at the end of this presentation. So to summarize, in fact, this alarm cause analysis solution, we have our two modules. So the first one with the graph is using the streaming data and the alarm co-activation period that is really useful to render all the possible causalities. And well, compared to the pattern extraction, it can show also the rare association and the rare causality that will not be catched by the pattern extraction, that will use a large set of data to extract the meaningful and confident pattern over time. So this solution is pretty interesting because it is interpretable. In fact, when we work with experts, when we work with, well, experts, in fact, they don't just want to be proposed an answer. In fact, most of the time they want to evaluate for themselves. They want to have the opportunity to see if the answer that is proposed by the machine learning model really makes sense. And this solution with the graph and well the pattern, the two are really complementary and help the end user to troubleshoot, to not only appreciate the cause we are proposing, but also to navigate on the graph itself and try to find out the right cause, and well, understand the issue to fix it in a quicker way. So thank you for your time and thank you for listening. And if you have some question, I will be happy to answer them.
Thank you so much, Maguette, for your interesting talk. So I heard it's your system is deployed.
Mm-hmm.
Yeah, so that's great. What is your experience in deployment? Like, what are the challenges and difficulties that taking it from research to deployment?
Yeah, so well, in fact, when we are doing so well from research to deployment, there is always a gap, in fact. For us, for example, for this particular project, we had a discovery time, so to research what was the potential solution we can offer for this problem. And well, we saw that with the deployment that, well, there can be some mismatch between what the client expect and what we are giving. And well, in fact, before deploying, we agree on all of this, but well, there is always mismatch. So in fact, a deployment is a continuous process, because we will find a lot of small things that will not apply anymore, because well, on a research step, in fact, we will just focus on some main example, and then the deployment will show the whole picture, and it will show the result on, well, all the hundreds and hundreds of cases. And well, for sure, it will show what are the limitation, and then well, this limitation has to be worked on. So yeah, it is a work in progress for a long period.
Yeah, thank you very much. That's very insightful, and it's very inspiring for us researchers, because we shouldn't stop at the research and seek to deployment and beyond
Yeah.
that. Yeah. So thank you so much. So one question from Sanjay. He's saying, thanks, nice work. How did you overcome the lack of labeled data? Also, did you use causality methods as in parallel methods?
Well, so in fact, in our domain, I think when we work most of the time with real world problem, it is hard to have human annotated data, expert annotated data. In fact, experts will always not have the time to give us this annotated data. So while for this project, we were focused on the cause alarm. And while we have multiple incidents, but in any way, we didn't have annotated cause alarm. So to be able to provide the right cause alarm. So in fact, most of the time, in fact, in data science, in companies, we are working with an unsupervised method. So we are trying to figure out a way to give the best solution using unsupervised technique. And then, well, bit by bit, having some first feedback, we can adapt and well adapt the methodology. And as for the second question, if we use other type of causality metrics, so no, in fact, we didn't. In fact, we had 3 months to discover what was the solution we could provide. So well, this is a limitation, so a time limitation. So yes, we explored the pattern to have meaningful rules over time, and then the causality, which we know that is true for the telecommunication, domain, in fact, to address this problem.
Thank you so much, Maguette, for joining us and for the amazing talk and the discussion.
Thank you very much for having me.
Thank you.